Implicit human feedback is the reactions humans give when they observe other agents. Such feedback is not intended to influence behavior, but nonetheless contains information about the agent's performance. Learning from implicit human feedback, abbreviated as LIFE, is low cost, since it does not burden the human user who naturally provides such reactions even when learning does not occur. To approach the LIFE problem, we ask the question that can an agent learn a task from implicit feedback it receives from its human user? You might be wondering, is there enough information from implicit human feedback to enable learning? In this video clip, the dark circle is an agent picking up color blocks in this grid world. Each color block is associated with different rewards that are observed by this human subject. The human observer is told that she will be paid by the amount of rewards earned by this agent. From seeing her reactions, we may not be able to say what exact rewards are associated with each of the color blocks, but we can infer their relative goodness with respect to each other. If we also know that there is only one color block that's associated with positive reward, we may be able to pick out the corresponding color. Now that we have a better understanding of the LIFE problem, let me introduce our proposed framework for approaching LIFE. EMPATHIC, standing for Evaluative Mapping for Effective Task Learning from Implicit Human Cues, is a data-driven approach that aims at learning mappings from implicit human reactions to known task statistics, and apply the learned mappings for learning deployment tasks when task statistics are not available to the agent. The EMPATHIC framework consists of two stages. In the first stage, implicit human reaction data is collected as human observers watch an agent performing the training task with known task specifications. Importantly, the human observer is not told to teach the agent, but is incentivized to care about the performance of the agent, such that their internal model of the task is aligned with the given task specification. Corresponding task statistics are recorded. Mappings from human reaction features to task statistics are trained in a supervised manner. In the second stage of EMPATHIC, when an agent is trying to learn the deployment task without explicit task specification but access to a human observer, it can leverage the learned mappings from the first stage to obtain predicted task statistics. To instantiate and evaluate EMPATHIC, we define the task domains and a way to incentivize the human observers. In this work, we focus on modeling implicit human feedback in the form of facial reactions and predicting reward categories. We designed two task domains, a simulated game we named Robotaxi, and a robotic sorting task. We recruited participants to observe agents acting in these two domains and tell them that their financial payout will be determined by the amount earned by these autonomous agents. We take 2 episodes of Robotaxi data from each participant for training a reaction mapping. We take windows of human reactions centered around pickup events and map them to reward categories. We leverage an existing feature extractor for processing the human reaction video data and extracted facial features. These extracted features are fed to a multilayer perceptron for predicting the corresponding reward category around that time window. We instantiate EMPATHIC with 3 different deployment tasks to evaluate our learned mappings in the first stage, including 2 in the Robotaxi domain and 1 in a robotic sorting task. We will show some results in the robotic task in the rest of this video. Detailed results of all 3 tasks can be found in the paper. In this task, the human observer earns $2 when a correct object is moved into the trash bin, but is penalized by $1 if a wrong object is placed instead. The robot's action differs a lot from the Robotaxi agent's action. Therefore, we modify the network to output a positivity score for a given window of reactions and average the predicted score across the entire trajectory and use that to rank different trajectories. The following are sample trajectories with the predicted positivity score visualized. Here is a trajectory with 0 return. And this is a trajectory with a positive return of 2. This trajectory results in a penalty of 1. The predicted rankings of these trajectories using our model corresponds well with the true rankings by their final return. Full details can be found in the appendix of the paper. Thanks for your attention.